Good morning, here we are at the physics video lecture. Physics 105A video lecture 6. And we're right in the middle of some great material. So I'm gonna write what we had last time. I'll turn it into a homework problem and then we'll keep moving. So we are talking about Newton's law in one dimension I'll be consistent here. So I'm not using the dots right here, so dx, dt, and t. So that's the general case of Newton's law, 1 degree of freedom. We got the mass here. And we've done a couple of examples already, so I'll just list them. We did F equals constant, and that's the really important one. Law of free fall is included there. And what we're seeing now is we're getting the results of this as our limiting case for the more complicated examples. So the next one, we had an F is strictly a function of time. And we did see with that particular example, we could take a limiting case of some parameter and come back to this case. That's what we're going to pursue as we move through this. My third example was F equals F of V equals, in this particular, and so I'll actually write that down again, what we had. We had m dv dt is equal to mg minus v times v. Okay, so v is that first derivative we're talking about, of course, and we wanted to integrate this. We had to use a technique called separation of variables. And there were a couple of things here, and this is what I ended with, and I didn't have it on the board at the time, but in the limiting case of this type of motion, when the right side turns into a zero, the left side turns into zero. That is to say, when you reach a terminal speed, then the acceleration is zero, okay? And so what do you have here? Terminal speed is equal to mg divided by v. And we found that as well for the time goes to infinity limit. So good, we have that, and I made an assignment on this as to taking the solution to this and taking the limiting case and returning to the free fall example. My next problem is also force as a function of velocity. We're going to take F of v is equal to mg minus v times v squared. So in both of these cases, b is some constant, and here you'll see it has different units, obviously. But this is the same type of problem, except instead of linear in velocity, it's quadratic speed. And I'll put a note here right away that the terminal speed for this problem is clearly going to be, based on what we just learned up here, mg over b square root. So you're going to want to get that as a result when you solve this problem. So homework, we're going to have m dv dt is equal to mg minus bv squared. It's as though we had the positive direction down, the way we talked about last time. So that's fine. I'm going to give you a hint here the way we're going to solve this is not for the time, but for the position dependence. So we're going to write this mv dv dx. As you recall, chain rule told us dv dt was dv dx, dx dt. Did that last time. So you're going to have mg minus bv squared v dv dx is equal to g minus b divided by m v squared. Okay, so you guys take it from there. You do the same separation of variables that I did for this case. And because of the form right here, you're going to find a simple substitution takes you to the answer. So since this is a homework problem, I'm going to write find. I'm going to give you two tasks here. Find v of x, because that's what you're going to get. The time dependence has been removed from this problem. So you want to find v of x. And the second point is to check the limit as b goes to 0. Because when you get the limit as b goes to 0, you're back to this problem, which was this one. Okay, you're back to this constant velocity problem, and we're supposed to find something like this: b squared equals b0 squared plus 2a x minus x0. That's the famous result for the one-dimensional constant acceleration, velocity acceleration position relation, okay, which we derived the other day in some form or another. We may have had f divided by m for this constant acceleration. So yeah, you can see we're still doing these limiting cases, and what we find is these expressions that we integrate up are kind of complicated, and you can't see the truth of them. That's why when we do this limiting case, as the friction goes to 0, we get back the standard free fall expression. So that's a major theme. Now this is where I bring the Taylor expansion into play. I'm going to motivate our discussion of the Taylor expansion, which will be the rest of this hour, in terms of what we did to take these limits. So last time in my example, I did an expansion. So for our limiting cases, for example, this one right here, so that's a homework problem. You could also leave room in your notes and put it in twice. You could turn it to me as a homework problem when you're done, and you could leave room in your notes to insert it into your notes as well. Be that as it may, for limiting cases, we used the Taylor expansion of a function. So that's not just a technique. In physics, that's really a way of thinking. And experience has shown me that the students could all use a review of the Taylor expansion and just the whole idea that's based on. So that's what we're going to do. We used it for this limiting case. You know, what did we have? We had e to the x is equal to 1 plus x squared over 2, x cubed over 3 factorial, and so forth. And I had just used the exponential function up to this term, and you guys in your homework assignment were going to have to actually go up to the second one as well. So it's an important mathematical tool, but it's, for us, it's really as important as the whole concept of the derivative itself. So what we're going to do is study them, and as a first, well, I have some examples But one of the examples I want to talk about after we've studied the Taylor expansion, could be this hour, could be the next hour, would be to go back to these forces as a function of speed and understand them a little bit better. Okay, so that's the plan. And our next task here is to talk about Taylor expansions. So this is an important, very important topic in and of itself. So this is a new section. And the way we begin is by just looking at a function. Begin with a function and its derivative. So we'll actually begin with the derivative of f. Derivative of function f of x. So I will draw some nice generic x, y. I've got some y equals f of x curve, and at some point here, x0, I'm just going to write down the definition of the derivative. Okay. So we have f prime of x 0 is equal to the limit x goes to x0 f of x minus f of x0 divided by x minus x0, right? Just the way it is in the book. Nice little red box around here. We can ponder this for a moment. Everybody's seen this before. We're out here at x0, and there's f of x0. Then, without taking that limit, we just have what are called difference quotients. And the numerator and the denominator are the rise and the run, so to speak, respectively. And in the limiting case, x goes to x0, these triangles get ever smaller and they're ever closer to the tangent to the curve at that point. So that's how we learn about the derivative. And the next thing I'm going to do is just talk about an approximation based on this. Namely, I'm going to replace the equal sign with an approximate, and I'm going to get rid of that limit. So good, let's do that. So everything is named star. So from star, we can do the following. In fact, I'm just going to write down what I'm going to do. I'm going to get rid of the limit sign, write an approximation here, and just solve for f of x. So from star, we have f of x is approximately equal to f of x0 plus f prime of x0 times x minus x0. Okay, so I've just solved that. No lie here because I wrote approximately. Okay. Yeah, so but what is this? In fact, if I didn't have the approximate sign, but if I had the equal sign, what would this be? This would be the equation of a straight line in the point slope form. Okay. So let's just go back to our graph. We have, roughly, I don't have to do the exact same thing. There's my x0, there's my x-axis. So what I have here as an approximation is the equation of the straight line f of x0 right here. Equation of the straight line that goes through that point and has the slope f prime. We'll try to draw that. So this is a picture where you're well advised to make a pretty big sketch in your notes. So what's approximate about this? The red line is this right here. It's approximately equal to f of x because f of x isn't a straight line. And the difference, I use another color here. The difference I'm going to kind of shade in. You can see the difference between the function and the straight line gets ever smaller the closer you get to x0. Okay? So at x0, of course, you have the function itself. If you keep x minus x0 sufficiently small, you have an excellent approximation to the function. On the other hand, if you let x minus x0 get too large, you're down here and you're no longer approximating it very well. So we have, what can we then say about this? The first derivative, well, one thing I could say is this is the first term of a Taylor expansion, or actually the first two. So just taking this form right here, we already have the first two terms of a Taylor expansion. So good, that's actually, if I find some clever words to write here, I've said them all already, right? What this all means here. So let's put this as a note. The straight line which is the right side of this, approximates f of x if x minus x0 not too large. And so what we're going to do next is ask about quadratic and higher order approximations. You can see what I've shaded in here looks kind of parabolic. So there could be a quadratic, there could be cubic, there could be higher order terms in here to get a better approximation. So we've got this approximation here. Better approximations with higher powers, with added powers of x minus x0. And so that's what we're going to do. Is find out how to get those higher powers. And in order to do that, we will now talk about just basic power series. Or we could say polynomial expansions. Next, consider, should I give this a name? F of x equals the sum of, well, first I'll write it down without the summation convention. So we're just going to put in some more of these right here. So f of x equals a sub 0 plus a sub 1 x minus x0 a sub 2 x minus x0 squared and so on. So we can also write this type of expansion as equals sum of a sub k x minus x0 to the kth power, k equals 0 to n. We have n of these. Or we could let go k equals 0 to infinity. And if we say k equals 0 to infinity, then it'd be the same as this thing here, just a sub n plus 1, and all beyond that would be equal to 0. So I'll go ahead and say k equals 0 to infinity. And you guys can put a note what I just said about n. And let's just take derivatives. F prime of x is equal to, you can actually do it on this sum here, but if we look here, you know, we'll kill the constant and we'll have a sub 1 plus 2 a sub 2 x minus x0 plus 3 a sub 3 x minus x0 squared plus and so on. And we can actually do the same thing in here. But I'll go ahead and write it out explicitly here. So f second derivative, sorry. Two derivatives, kill that one, we have 2 a sub 2 plus 3 times 2 times a sub 3 x minus x0 and so forth. And the third derivative, because the pattern you'll now get just with simple induction. You're going to get rid of this one, you're going to have 3 times 2 times a sub 3 plus higher order powers. You're always going to have this constant, and then the next term will be linear in x minus x0 and so forth. So from this, we see that a sub k is equal to f kth derivative of x0 divided by k factorial. You see it here on a sub 1, a sub 2, and so forth. Okay. The second derivative is going to be divided by 2, give you your a sub 2. The third derivative divided by 3 times 2, give you your a sub 3, and so forth. So, I should say one more thing. I have to evaluate these at x sub 0. So if I evaluate f prime at x sub 0, I just got the a1. Evaluate f double prime at x sub 0, I just have the 2a2 because that goes down, and so forth. Okay. So that is our result just for some series that we wrote down like this, polynomial series. And that gives us the Taylor expansion. So now we've found f of x is equal to the sum k equals 0 to infinity kth derivative x0 k factorial x0 to the kth power. We're going to write that out again, of course, but this is the compact form, very nice for remembering this. Okay, so it's not hard. Formally, we have this thing. We need as many derivatives as we have powers of x in this thing. And there are cases where you only need a couple, and there are cases where you need all infinity of them. So let's look at that. And in fact, I'm just going to write out a few cases of this now. in keeping with what we did right here. And as you'll see, the linear case is exactly what we had right here. And then we'll just add a couple of those as well. Let me consult the clock here. Okay, excellent. So I'll write a few of these out, and then we'll do a couple of interesting examples to bring us back to physics eventually. But right now we're just putting these I'll do the first, second, and third version of this. So we can have f of x0 plus f prime of x0, x minus x0. Okay. And I'm putting an equal sign here. Maybe we just have a function that is a straight line. Okay. But 1/2 f second derivative of x0, x minus x0 squared. Well, what is this but your general parabola? General parabola here, x minus x0 squared, and 1/3 factorial is the next one. At some point, instead of little primes, you just designate it this way, x minus x0 cubed, and on and on. So one way to look at this is I'm getting an ever better approximation. So if I do my function here, maybe I'll do a different one. I'll do that one there right now. This is kind of an interesting one. We'll make this the x0. Then my linear approximation is if I just go f of x0 plus f prime, and that is my straight line again. Okay. But if I want to go further away from x0, I'm going to need this quadratic term, and it looks like the second derivative will have a minus sign, right, to pull this down. In fact, let me even, gives me a good idea. Okay. So let's actually accentuate that. So we've got an up curve and a down curve, and I'm going to put the x0 right here. Okay, so here's my point. There's my straight line that goes through there. And yes, now you can see, without a doubt, first derivative straight line, I add this contribution, and then it's some concave down parabola here. But we don't know what's going on beyond here. So I would say to within that range, I just cut this thing off right here. Okay. But if I have, if I want a larger range, you can see it's swinging back up there. I'm going to need more of these terms. But stopping it with the quadratic is pretty good. It's very common in physics. And then you go beyond your straight line into your quadratic. There are also examples where you need all infinity. And sometimes if you have them and you have them in the form of a power series, you can do differentiations and integrations really nicely. So this is an example, and it's discussion where I'll just put a note right here, note for this range, take up to the second order terms. When we talked about order, one way to discuss this, we would say this is the 0th order, the 0th derivative, this is the first order term, this is the second order term, and so forth. So we'll take up to second order terms. Let's see. Good, so that's the way to look at these. And in physics, we often just expand to linear. We get a lot out of expanding to linear or quadratic terms. And so, the Taylor expansion, all infinity of them, not threatening at all in that regard. Okay, so I have a nice example. Let me check the clock, see if I have time for it. Yes, of course we do. Yeah, this next example will take us back to physics and geometry. So this is going to be a concrete example. So I'm going to begin with a circle. Or here's what we're going to do. So we're going to have x and y, and we have some curve that has a local minimum here and goes up like that. Okay, so that's a curve. And what we're going to do is take the circle that nests in this thing. Okay. The idea here is that that circle nests perfectly in that curve right at the bottom. And then, eventually it changes a bit. So we're going to get the equation of this circle of radius r. And then what we're going to do is have the circle and then the curve, the function of this curve as well. Okay, we're going to relate this function to the circle. So first we'll start with the circle. And we know that x squared plus y minus r squared is equal to r squared. And so we'll just extract y minus r squared equals r squared minus x squared. Y is equal to r minus root r squared minus x squared. So that's our function. We took the minus sign here. When x is equal to 0, y is equal to 0. Okay, so that's the lower half of that circle. The plus sign here in the square root would have been the upper half. Okay, so y is equal to r minus root r squared minus x squared. Okay. Now let's expand y of x in a Taylor series. So here, like to number things. So that's 1, 2. Expand y of x in a Taylor series. So what do we have here? We have y of 0 is equal to 0. So let's go ahead and write y prime of x is equal to minus, and then I have the square root here, so 1/2 root r squared minus x squared times negative 2x is equal to x over root r squared minus x squared. And we see that y prime of x equals 0 at x equals 0. So y prime of 0 is equal to 0. And of course that makes sense. It's the red curve. It's got a minimum right there. Now let's do the second derivative. Y double prime of x is equal to 1 over root r squared minus x squared plus x. We've got this to the negative 1/2 power, so negative 1/2 r squared minus x squared to the 3/2 power in the denominator and minus 2x in the numerator. under here. So now, we see that y double prime of 0, right? When we put the x equals 0 over here, this whole thing goes away, and it's just 1 over r equals 1 over r. And here's what we have now. Y of x for that circle is equal to 0 plus 0 plus, well, 1/2 1 over r x squared. So a circle, like that red circle, goes up quadratically at the beginning, and its second derivative is equal to 1 over r. Second derivative is the curvature of the circle, right? The inverse of the radius, so radius of curvature. And we'll leave that right there. So what about the function? I guess I should name these now and make sure. So this red one was my y of x, and this blue one I'm going to call my f of x. Okay. So the blue curve, or the circle nests here in the blue curve. And also we have our f of x, which is 1/2 f double prime of 0 x squared, simply because that's the Taylor series in general. So what do we learn? The second derivative at a local minimum gives us the curvature of that curve, the radius of curvature. And you can even imagine that, and this is something you guys know from mechanics in the past, we'll do it more, but suppose you're calling this a roller coaster, you come through here, and you're going to have that v squared over r acceleration, right? That would be the same 1 over r from your v squared of r acceleration. So this would also be the local curvature of that roller coaster. It could be changing the whole time, but right there at the bottom, it is curvature, is 1 over r. And therefore, when you're doing physics and dynamics, that would be what you take. You just find the second derivative there, and that's your local radius of curvature. So, that is also an important point. Second derivative at the local min, and of course the maximum would be the same thing, gives radius of curvature. Okay, good. Once more, let's consult the clock. I'm going to do a couple more applications here. And I'll call them homework, and I'll just kind of work them with you. Again, this is the kind of thing you could leave room in your notes and have it in your notes as well. So what we want is a couple of Taylor expansions. So expand f of x equals e to the x, f of x equals cosine x, f of x equals sine x in a Taylor expansion. All infinity of them in Taylor expansion, Taylor series. All right, all infinity. And this goes very quick because the cosine, you do the first 4 derivatives and then, or the first 3, and then you cycle back. Okay, so there's an induction that allows you to very quickly write the answer down. Same for the sine, you take 3 or 4 derivatives, you know, it's 1, 0, minus 1, 0, that kind of thing, and then you have that, e to the x, because all derivatives are just, you know, it's always e to the x, e to the x, e to the x, evaluated at 0 is equal to 1, so expand about around the origin, all right, that's what I'm around x equals 0, these 3. So you really know these, write them down, all infinity of them. Let's do another couple. I will just, you know, in fact, I'll just give one answer. You can do, it's one example. You can do as many of these as you're interested in. This last example, and this is also homework, but I'm pretty much doing it. Expand f of x equals the square root of 1 plus x to third order. Okay, you want to expand it to third order. Let's just get started on this one. This one's interesting. First of all, the graph of the square root of 1 plus x. So we're just going to say for x greater than minus 1, and we know that it's going to be that kind of thing, except it doesn't get that flat, right? It is going to keep growing, but it's a square root. Okay, good enough. Let's do f prime of x is equal to 1/2 root 1 plus x. F prime of 0 is equal to 1/2. Okay. So f of x, or just the square root of 1 plus x, which is f of x, is equal to f of 0, which is just 1, plus f prime of 0, 1/2 x. Okay. So that is just this line with a slope 1/2. Okay. And this is interesting. You can use this to get approximations to square roots. Okay. So I'm going to have you do a couple more orders just, you know, to do it. But if you just have this alone, you can get approximations to square roots. So I'm just going to end with this example. The square root of 10 is equal to the square root of 9 plus 1 is equal to 3 square roots of 1 plus 1/9, right? Get a 9 cancels that. So now is where we would apply what we just learned. So we would have 3, and now I'm going to call it an approximation, approximately 3 times 1 plus 1/2 of 1/9, 3 times 1 plus 1/18. Okay. Equals 3 and 3/18, which is 1/6. 3 and 1/6. And if you plug that into a calculator, you're going to find it's a pretty darn good approximation. And you know, you've got your intuition here, what was going on right there. And yeah, so that's an example of the usefulness of these type of little expressions and expansions. I'm going to leave it right there, and see you guys next time.